So officially, this is a 45th Flow seminar. My name is Samuel Horvat, and together with Peter Richtárik, Virginia Smith, Avril Bellet, and Dan Alistar, we are the organizer of Flow Seminar. For those of you who are attending for the first time, Flow Seminar stands for the Federated Learning One World Seminar, and it was created as a global online forum for the dissemination of the latest scientific research in all aspects of federated learning. This includes both theory and application in areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization, systems, or hardware. For today's talk, it's my great pleasure to introduce our speaker and also one of the co-organizers of the seminar, Peter Richtárik. So Peter is a professor of computer science at King Abdullah University of Science and Technology, where he leads the optimization and machine learning lab. His research interest lies at the intersection of mathematics, computer science, machine learning, optimization, numerical linear algebra, and high performance computing. And he is one of the original developers of federated learning. Throughout his career, he has received many awards, among them Best Paper Award at NAVRIPS 2021 in Federated Learning Workshop, and also SIAM SciGES Best Paper Award. And today he's going to talk about his new work on a new, simple, theoretically better, and practically faster error feedback. So Peter, please, stage is yours.
Thank you very much, Samuel. And thanks to me for inviting myself to give the talk in Flow. And one of these prizes that you mentioned, I was joined with you. So I have to say thanks for the very nice collaboration there. So today I'll talk about something we call EF21. 21 is because it's year 2021. So it's error feedback mechanism, which is up to date as of this year. And we claim this is new. So this doesn't just boil down to something that existed before. We claim it is simpler in some sense, simpler to understand, simpler to analyze. Theoretically better. The theory is better in several ways, and I'll talk about that in some detail later on, than existing theory for error feedback. And it's also practically faster. So in some sense, what we're trying to say by this paper is forget about error feedback as you know it and think about EF21 instead. This is joint work with two great collaborators, with Igor Sokolov, who is a student at KAUST, and Ilyas Fatkulin, who is an intern at KAUST and a student in Germany. The paper is already online or archived, so you could go ahead and read it if you wish. And for those of you who attended my short talk at the Fairy Learning workshop at ICML, this is essentially the same talk. I added a few slides, but I only had 20 minutes, including questions back then. So you can see why I'm talking for this long on the first slide. I don't have slides really for a full hour. So we'll be just discussing things more slowly, taking them more slowly. So that also means please interrupt me, ask questions. It'd be very nice to have some back and forth. Good. So the first part, as usual, is introduction. And we'll be dealing with this very basic fundamental problem in federated learning, and that is to train a supervised machine learning model on n devices. So you can already see we're in the cross-silo setting and not in the cross-device setting. You could think you're in the cross-device if n is very large. On the other hand, the method I'll describe doesn't allow for partial participation, so you can better think of this as a cross-silo federated learning setting, or you can just think of this as distributed training of a supervised machine learning model. We have d parameters, n devices, and function fi is the aggregate loss function over all the data stored on device I. So this could be very complicated function based on millions of data points or few data points. These distributions could be arbitrarily different. In particular, there'd be no assumption on any type of similarity between these functions. Okay, so this is the very simple description of the problem. There'll be no difficult additional setup such as non-smoothness. Things will be smooth. I don't have any proximal term here. this is it in the full generality we consider in the paper. In order to motivate what I'm going to talk about, let me first describe the most basic of all methods for federated learning, and that is gradient descent. So some people say these are local methods are the most basic methods of federated averaging. This is not how I think of it. The most basic method is gradient descent and distributed version of it, and all other methods are some additional tricks applied to the gradient descent to make it faster, better, more secure, private, and so on and so forth. So we better start there. So what we have here, we have a current model XT, and from it we subtract a multiple with a constant gamma of the average of all the local loss of the gradients of all the local loss functions. So gamma is a constant step size, and indeed in this talk I won't have any adaptive or decreasing step size strategies. Just a fixed step size will suffice. So let's look at how this works in a distributed scenario, because this is where the bottlenecks will appear. So here's an example with 3 machines. The first machine owns function F1, second machine owns function F2, third machine owns function F3, and all of them at the beginning of the tth iteration own a copy of the current model, which is xt. And remember, this is a d-dimensional vector, and d is typically very large, because in overparameterized regime, d it would be even bigger than n, and n could be very large. So then each machine, each device, each computer worker computes their own local gradient, and this d-dimensional vector is sent to the server, and the server performs averaging. You can see this average over these 3 vectors and takes a gradient step. So the server here takes the gradient step. You could send the average of these gradients back to the machines, and then the machines can take the gradient step. It doesn't really matter, but here I'll just think of the server as taking the gradient step, and then the server will broadcast xt plus 1 back to the machines, and the process will be repeated. So what is the bottleneck here? So for simplicity, I'll assume that the bottleneck here is the communication of these huge dimensional, d-dimensional gradients from the machines to the server. I will assume that server can broadcast the model very, very quickly. Now, this does happen in some situation where the broadcast is much faster than this communication from the machines to the server. But if you are not in such a situation, you can think of this as some sort of a basic scenario which should be enhanced by some sort of compression or some sort of communication reduction strategy, which also does something about the communication from server to the machines. But I'm not going to talk about anything like this. And we have at least some people in the audience who have worked on bidirectional compression, so you know what I'm talking about. But here I'm just assuming broadcast is going to be easy. Another way to think of this is that you may think that server doesn't exist at all, but then we're not in the federated learning setup, and you can think of the server being just a virtual computer, where in fact the server means this is all the computers. So this communication from machines to the server actually means from machines to all the other machines. So you can think of these devices as living on a fully connected network where every device is connected to every device. And then there is no need to communicate this model broadcasts by the server back to the machine, because the server doesn't even exist. So you can think of any of these abstractions. The point is, these orange things are the bottleneck, and we need to do something about that. And one of the most basic strategies, and I'll ignore all the other strategies, for reducing the dependence of the algorithm on this is communication compression. So you could work with acceleration, you could work with local steps, as in local gradient descent, local SGD. You can think of many other strategies, adaptivity, and so on and so forth. But the purpose of this talk is to talk about a fundamental problem in communication compression for gradient descent. So we'll work with distributed compressed gradient descent, DCGD. And it's this method. There's a very simple adjustment to gradient descent, which is I'm inserting this calligraphic C in front of the gradient, of the local gradients, which simply means I'm applying some sort of a compression operator to the gradients. And the idea is that if you compress the gradients, you have less information to send than, let's say, 32 times d bits. So it could be, let's say, 9 times d bits, or it could be, you could have sparsification, you could have all kinds of strategies, even combined sparsification and quantization. The point is that sending the compressed gradient is much cheaper from the machines to the server than sending the full gradient. And a particular feature of this talk is that I'll talk about the general class of compression operators, which are called contractive compression operators. Sometimes they're called biased compression operators. They have different names, but the idea is that this is a mapping, possibly randomized, which satisfies this inequality for every V, and some constant alpha, which is going to be strictly positive. Could be 1. In case this is 1, C is identity mapping, so we're not compressing at all. But in general, it's not 1, so the right-hand side cannot be set to 0. This left-hand side here, you can call this the error in some sense, or distortion or something like this. And the right-hand side bounds the error that you make by compressing vector V to CV. All right, so then the method looks like this on this picture. Is the same method as before, so gradient and send, but now with compressed gradients. So everything is the same, except now we send compressed gradients, and that is much cheaper, and this is what gives the boost to the method. Now you average, you aggregate the compressed gradients, you broadcast back the xt plus 1, and so on and so forth. So this is the basic idea. Now, unfortunately, this doesn't work. It does work for a more narrowed down class of compression operators, so-called unbiased compression operators. This works in a certain sense, but for this general class of contractive compression operators, which are very popular because, let's say, the top K sparsifier belongs to this category, this thing can diverge. And in fact, it can diverge exponentially. So this is the major issue with distributed compressed gradient descent with this general class of contractive operators. And for an example for why this can diverge exponentially, I recommend that you look into this paper from last year of Beznosikov, Samuel, who introduced me, Mary Safarian, and myself on bias compression for distributed learning. And we have this very simple example. It's included here in full. So this is the full example. In 3 dimensions with 3 machines, you have 3 strongly convex functions, and you can write down a formula for the kth iterate, and it turns out you have some positive number raised to the power of k times the initial iterate x0, so this thing will just diverge exponentially, even though we know the solution here is. Okay, so this doesn't work, and now the question is, what does it mean? Should we not compress at all? What should we do? Well, in fact, there is a mechanism that was proposed already in 2014 for fixing this issue, and that's how I like to think of error feedback. So error feedback is a mechanism for fixing the divergence of distributed compressed gradient descent, which may happen with this class of contractive operators. So this is a very famous paper by now by Frank Seid and co-authors, as you see from 7 years ago in Interspeech 2014, and you can see here right in the abstract they mention if the quantization error is carried forward across many batches, they call this error feedback, and so on and so forth. So they gave this the name error feedback. The paper is very influential, already almost 600 citations, and many people are working on understanding this method, because in this paper, the method was suggested, proposed as a heuristic, but it was not analyzed. And in fact, the analysis is lacking even as of now. We know much more than 7 years ago, but still not enough to really understand the method properly. And this is why we have a paper, we had some job to do. So error feedback is this method. When I gave my ICML workshop talk, I said that I don't have much time, so I will not elaborate on it too much. Now I do have time, but I still didn't create new slides explaining what error feedback means. So maybe I'll just use this slide to explain it. In case you're not familiar with what this method does, you could just simply ignore at all the detail and only accept that error feedback is some mechanism which fixes this divergence. So you still communicate compressed gradients or compress something d-dimensional and compressed, but it's not, you're not running this method, you're running this method with so-called error feedback, and then the method will not diverge. So here's the pseudocode. So what happens here at the beginning, the error is 0 on every device. So all the errors are green here. All the gradients are red, and the estimates of the gradients through error feedback are blue. These are the W's. So there's no error because nothing has been communicated yet. And at the beginning, every node computes gradient estimator, and gradient estimator is blue WI0 is going to be compressed gradient. You can ignore for a second that I multiply here the gradient by the step size. In some sense, you could take the step size out, but here it's done this way. So it's compressed gradient or compressed scale gradient. And this is what will be sent instead of the actual gradient. And now, because you wanted to send the red stuff, but you actually sent this blue stuff, there is a difference between the red and the blue right here, right? So this is what you wanted to send. And I hope you can see my pointer here. The red stuff you wanted to send, and this is what you actually sent, which is the compressed version of this. So there you made the error, and the error is the difference. Now, the previous error here, EI0 was 0. So at the beginning, this is not there. So you can ignore it. But this is how you define the error. Now, in the next iteration, you will have some error which is accumulated from previous iterations. So that's why this is there too. So you just keep adding new error to the previous error always. Okay, so the green stuff is the error. And then the idea is that next time you're going to communicate, you don't communicate just what you want to communicate, the freshest, newest gradient, which is this, but you add to it the error from the previous iterations. And that's what you compress, and that's what you communicate. So that becomes the new W. Okay, so the generic idea is simply you want to communicate new gradient. Okay, fine, but you add to the error which was accumulated in the previous iterations, and that's what you compress, and that's what you send. But by doing that, you've made another error, and you just keep adding that error and progressing from iteration to iteration. All right, so maybe I'll pause here in case there are people here who have never seen this method, because we are going to be improving this method. Now, on the other hand, I will not improve the method in such a way that you need to know what this method does, because the new error feedback just looks very different from this. So you don't really need to understand any detail here in order to understand the new error feedback method, which we call EF21. But in case anybody is interested and doesn't know, have not seen this before, has not seen this before, please go ahead and feel free to ask. I'll pause here for a moment.
Just as a reminder, please, if you have any question, either raise your hand or put your question to chat and I'll try to unmute you.
Okay, so there's a question.
There is a one raised hand.
Kumar.
Hi, can you hear me?
Yeah, I can hear you, Kumar.
Yeah, so in the assumptions, the like contraction map, the upper bound had fixed alpha, right? So throughout the talk, we are going to assume that alpha is fixed in our compressor, right? It's not going to change.
It will not be changing. So there's a fixed contractive factor. So this alpha is uniform in all V's.
Right.
So for some particular V, maybe there's a better alpha, but this is in some sense the worst case alpha that you can get.
Yeah, and even between like communications, it's not going to change.
So this alpha is just a property of C. So I actually apply C itself, okay? And if C compresses more than whatever this alpha gives you, that's fine, because I'm not applying this upper bound in the algorithm anywhere, right?
Right. So if it's like top K SGD, then you fix the K a priori.
Yeah, I
so
fix the K, and then I just apply top K, and it does what top K does. And this is just property of top K, that alpha in that case will be
K by D.
1 over K. Oh, so sorry, K over D.
Right. Thanks.
Right. Okay. All right. So I'll keep going in case anybody has questions about anything before this. Just feel free to ask. All right, so this is our feedback. It looks nice, but unfortunately, we don't understand all that much about it. We do understand much more than 7 years ago. In fact, we understood almost nothing even 2 years ago. So the existing theory, and there's just, let's say, a dozen or a few dozens papers with new theory for error feedback, has strong assumptions or even unreasonable assumptions, you could say, such as bounded gradients. So you may assume, let's say, strong convexity in conjunction with saying that the gradients along the path of the iterates are bounded. So this is a non-standard assumption in optimization because you can't normally check it before you run the algorithm. So it's algorithm run dependent assumption, and this is always problematic because then it puts into question whether this theorem that would lead from such an assumption is actually valid, because you are writing down a theorem about an algorithm, but then you assume that something happens during the algorithm, and maybe that doesn't happen, right? Or that the compression error remains bounded. Okay, so here the property of this contractive compression operator is this. This doesn't say that this compression error is bounded, because I have a bound which is multiplicative in the square norm of the input, right? But this doesn't mean that I can bound this right-hand side uniformly throughout the iterative process. If I can, then yes, the compression error remains bounded, but if I can't, then I assume it, and it may not actually be satisfied, or better said, we don't have a proof that it could be satisfied. So that would be problematic, such an assumption. Or single node setup. Of course, if you don't understand the single node setup, you shouldn't think about the multiple node setup. But in the single node setup, you don't really need error feedback. So this counterexample that I mentioned in this Beznosikov paper really needs to go into multiple nodes, because at least in the strongly convex setup, in the single node regime, you don't need error feedback. It turns out you can just work perfectly fine with the contractive operator, and you can see proofs of this in this paper. So error feedback, and not even mentioning that you don't need any error feedback or compression in the single node setup, because you don't have a server to communicate to, so you don't have any communication issues. So why would you compress, right? So so analyses which focus on single node setup are of theoretical interest, but they don't really attack the heart of the problem, which is the distributed setup, which is why we do compression and error feedback in the first place. Or many people would assume homogeneous data regime, so which in an extreme case could mean that all the functions fi, all these local functions, are identical or very, very similar. And this is rarely the case in distributed training, and let alone in federated learning. So these are very strong assumptions. And even with these very strong assumptions, and of course, I'm not saying that all of these assumptions are made at the same time. So sometimes it's just one of these, or multiple, and so on. But there's at least one of these which kicks in. And even with these types of strong or even unreasonable assumptions, the rates that we have at the moment, which is great that we have some rates, because there were no rates a few years ago. So these were really breakthrough works. We don't have any linear rate in the strongly convex regime. And everybody knows that gradient descent converges linearly for strongly convex functions, and many nice versions of gradient descent would converge linearly in the strongly convex regime. But with error feedback, you don't get it. You do get it with additional assumptions. So maybe if you assume over-parameterized regime, or if you assume you're in the single node regime, or if you assume that that you are not in the over-parameterized regime, but you are not running error feedback anymore. You run a different method, which kind of looks like error feedback a little bit, but you introduce some unbiased compressors again. But that is, in some sense, some sort of cheating, because for unbiased compressors, the theory is much better, much stronger. So by making things unbiased in some sense, it's expected that you get stronger theory. So these biased compression operators, these contractive compression operators, which are not coming from unbiased compressors, are hard to understand in isolation. Okay, and
yes, sorry, Peter.
Yeah.
Yeah, we have one question in chat by question. I'll try to unmute him.
Right. Thank you, Samuel. My question is, for DCGD, do we actually have some theory for bounded gradients? Does the counterexample essentially use that the gradients are unbounded?
So I have on the next slide some theory, which is not ours, but theory of some other people, where people assume bounded gradients, and then they get indeed some rate. And if you look at the counterexample here, so let's go back to the counterexample, you could see what happens. So the gradient is always the iteration counter times some fixed vector. So the gradients just go unbounded to infinity.
Okay, thank you.
That's exactly what happens here. Right. So if you don't assume strong convexity, so if you assume just smooth non-convex regime, then the best rate you can get is 1 over t to the power 2/3. Not you can get, but that you do get in existing papers. And you would expect that you should get 1 over t. And here, 1 over t means that the expected squared norm of the gradient is upper bounded by epsilon, not epsilon squared. So that's what this t to the power 2/3 means. So then you would expect to get 1 over t rate, not 1 over 2 t to the power of 2 rate. Okay, so you don't get, so now the question is, what can you do about this? And what we actually do, we fix all of this. We scratch all of these assumptions. We only will have standard assumptions, and we also resolve these issues. So you get 1 over t rate here, which is what you would expect, because that's the kind of rate that you would expect for gradient descent. And you also get the good linear rate in the strongly convex regime. In fact, the rate specializes to the rate of gradient descent if you do no compression. All right, so this is quite a good chunk of not complete picture, but I would say almost complete picture. If you know of some other works, please let us know. And I know some people already send us email and we missed a paper or two. So this is good chunk of the work on error feedback, which contains theory. And this goes back to 2018, Sebastian Stig and co-authors. So you can see the first theory only appeared 2-3 years ago. Then Sebastian and Sai Praneeth, and so on and so forth, all the way to 2020, Anastasia Koloskova co-authors, and so on. So some papers consider the strongly convex regime, which is this first column. Some papers consider the non-convex regime, and some papers consider the distributed regime. So I try to include only papers, or mostly papers that include distributed regime, because this is what we are interested in. There are more papers which do some analysis in the non-distributed setting. So I just gave here a few for illustration. And in our work, we're interested both in the non-convex regime and strongly convex regime and the distributed setting. And we don't want to have any limitations like this. So for instance, here the limitation is bounded gradients. And in the strongly convex case, there's no linear rate. Here, obviously, is the single node, single node, single node. There's some moment bound here. Here you have linear rate only in the overparameterized regime for strongly convex functions, and so on and so forth. And here, for in the non-convex regime, you don't get the 1 over t rate, but you get 1 over t something worse. All right, so this is a very, very brief overview. I apologize if I missed some, and I promise those at least who let us know that their work is missing here, we're very happy to add this in the revision. Okay, so now how do we solve all of these issues? And again, what the issues we want to solve, we don't want to have any strong assumptions, and we want to have the rates that you would expect. So the kind of rates that you would get from gradient descent in terms of the iteration count. And this is what error feedback 2021, EF21 does. So let me try to motivate how we actually get there. So we have a distributed compressed gradient descent, which is this method. So I started with it. And we know it can diverge, as I said already. And the example is this 3-dimensional example, 3 devices. And the example actually worked with the top 1 compressor. And then the gradients diverge exponentially. as Konstantin noticed. And if you do this, this thing can not work, and you have to apply error feedback. And our idea, from one perspective, can be understood like this: that what we want to do, we want to run a method which is almost the same, but we replace the C by something which we call C sequential. Okay, so and it seems as cheating at first sight, but I'll explain it's not actually cheating. So we want to run this method now. And in fact, our method EF21 is this method. So all that you need to know is what is C sequential. So that's what many slides now will be about. What is this? And C sequential should somehow be related to C, right? Because the issue here is that C is this contractive operator, which is not unbiased. And I don't want to simply just C sequential is going to be some unbiased operator, nothing to do with C, and then because then this is just a completely different problem, right? So C sequential should be a compressor defined in such a way that whenever I communicate, I still communicate with this compression operator. I still use C. So C sequential is somehow generated by C, but I don't necessarily compress the gradients. I may compress something else, okay? And I call it C sequential because this compressor will not, in fact, be defined in such a way that I just apply to the gradient. The compressor is smart, it's Markov in a certain sense. It looks at the previous gradients and the compressed gradients and is defined in a Markov fashion. So the C sequential is an adaptive compressor which evolves in time. Okay, so this is what we want. So now I'll describe C sequential. So the first idea towards C sequential is to just realize what are the issues with not going C sequential, which is going with the C. So the issue is this, and first let me draw this. So C sequential should be something like this. So we have a sequence of vectors that you want to compress. And now you want to define what will be the compressed version of the first vector or zeroed vector first, t vector, and so on. So this is a slightly different problem than just saying, okay, I have one gradient, what should I compress it with? And I just have some compression operator which is ready. So here we define we construct the sequence of compressors which evolve in time so that they are applied to a sequence of vectors. Okay. So, and what we want, and I'm just summarizing what I said before, C sequential should somehow be defined through C. And what we want this error, and I'm using the word error because error feedback deals with this kind of an error, which is the error between what you want to send and what you actually send, the compressed version. I want this error to converge to 0. Okay, so now the first naive idea would be that C sequential will just be C. You always use the top K, let's say C is top K, you always use top K, apply to the local gradient, and that's what you communicate. Well, if that happens, there's really no reason for this error to vanish in time. And you can see that quite easily from the definition of the class of compressors, C. So we know that the error is upper bounded by 1 minus alpha times the square norm of the input. So this, you get a guarantee for this to go to 0 only if the input goes to 0. But there's no reason for the local gradients to converge to 0 unless you're in the overparameterized regime. So generally, you're not in the overparameterized regime. And for that reason, these local gradients could potentially converge to any vectors. And then applying compressor C, which is contractive, to such vectors, which could be large in norm, will introduce really huge error. So that's a problem. That's the problem with this naive idea. And this is what the original error feedback from 7 years ago, 2014, is trying to solve. Now we have this other solution. So let's introduce a different idea. And the idea is, we'll now assume that we know something about the sequence VT. It's just not any old ordinary sequence, but it's a convergent sequence. Okay, so I'm abstracting from gradient descent. I'm not even talking about gradient descent anymore. I'm talking about a sequence of vectors which converges to V star, and assume that you know the limit. Now, of course, this is strong assumptions. You cannot really assume it in practice, But from a theoretical perspective and conceptual perspective, this is very, very good abstraction. So what we're going to do, we're going to shift this bias compressor by this optimal limit point, and then we kind of unshift it outside. So such a construction already exists and was proposed in 2019 by Konstantin Mishenko and co-authors, and it's called the Diana method. But this was proposed for unbiased compressors, and then this shift evolves in a certain way using essentially SGD. So here, the way you could think of this, this is the first type of a shifted compressed gradient method, which works for this class of contractive compressors, the general class of contractive compressors. All right, so why is this shift good? Well, intuitively, the shift is good because if VT converges to V star, okay, and that's the assumption, then what is inside this compressor converges to 0. And because we know that the error of the compressor C, because it's contractive, is upper bounded by 1 minus alpha times the square norm of the input, this will, the error will diminish as T increases to infinity. So here is a very quick proof. So this is the error. Now you write down the definition of C sequential is this. You reshuffle a little bit, use the definition of C, and you can see that you get an upper bound here, 1 minus alpha times the square norm of the difference. But this difference, this norm converges to 0, and that's why this compression error vanishes to 0. In fact, this would converge to 0 even if you didn't have a contraction, but you had any constant here, any positive constant, not necessarily 1 minus alpha, but 10,000, let's say. All right, so this is great. And intuitively, because the compression keeps vanishing, you make less and less error as you proceed, and this is what corrects the error. So that's the error feedback. This is the mechanism for reducing the error. Now, it looks like we solved the problem. In fact, if we could run this method, this would be great. Unfortunately, it's only of theoretical interest because we don't know V star, and that's the main limitation. And that's, in some sense, the only limitation. We don't know V star. So what do we do? So I'll stop here for a minute or two in case there are any questions. Let me see if I can see the chat. Okay.
And there are no questions at the moment.
I'll still wait. I'm pretty sure 1 or 2 will appear. Yeah, so I'm very well known for being able to introduce awkward silences in my talk. So I'm doing the same thing again. Thank you, Konstantin, for the nice remark.
Can you maybe comment? Oh, we have a question from Rustem. Please go ahead, Rustem.
Hello. So my question is, could you please comment on the connection between your error feedback mechanism and previous works? I mean, could we, for example, say that in some cases this sequential compression operator is the same thing that previous works use?
Right. So I didn't define it yet. I'll define it on the next slide. So the EF21 is still not this. EF21 is a version of this when we replace V star by some approximation of V star, which we can actually compute. And that's what EF21 will be. And I will also have a slide on explaining how this compares to error feedback as an algorithm and also theoretically. So I will do that. Just bear with me for a moment. Okay, so maybe I'll go to the next slide then. So EF21 is really the result of resolving this issue with this method in the following way. We just get rid of V star because we don't know V star, and we replace this by the last estimate of V star, which is going to be the C sequential applied to the last, to the previous vector in the sequence. So this is really the idea here. So we hope that the C sequential has this good property that its error diminishes. And since its error diminishes, if we construct it well, then C sequential should converge when you apply it to VT to V star 2. Okay, so this should be better and better approximation of V star as you go on. So it's not unreasonable to do this. But suddenly this is already something that you know, because you are constructing this is C sequential, so you know the previous one. So you could throw it in there, and this is really the definition now of C sequential. Okay, so if you put everything together, this leads to the definition of what we call the Markov compressor. And we call it Markov compressor because we construct it, and it has a Markov property that it evolves, and compressed version of VT depends on the compressed version of VT minus 1. Okay, so we have compressed version VT minus 1 here, compressed version VT minus 1 here, and then the C right there. Okay, so hopefully this is going to work. And if you put it together, you get this pseudocode, which we call EF21. So you can think of EF21 as being this method right here. Let me go back. As being this method on the bottom with the C sequential compressor that I just defined. Another way to write it down is write it down explicitly as a pseudocode, and it looks something like this, but you could ignore it. So it's easier to think of it this way. And this is, again, just the definition of C sequential. And you apply this independently and individually on each node for the sequence of local gradients. So that's the point. All right, so this is EF21. Let's look at it in the single node setting, because then the method is just very simple to describe. So it takes this gradient type step where GT is the gradient estimator at time t, and the gradient estimator evolves in this way. So it's the previous gradient estimator plus the compressed version of the difference between the latest gradient and the previous gradient estimator. So this is somewhat reminiscent of the Diana method, except in Diana, this shift GT is not equal to the gradient estimator. So this GT here, gradient estimator, and this shift here in these two places are two different vectors, and they evolve according to their own rules. And C also, in that case, needs to be unbiased for the theory to work. But here we don't need it, and the shift is exactly equal to the last gradient estimator. All right, so we have some extensions in the paper which I will not talk about. So we have a more aggressive variant, which we call EF21 plus. What that one does, it tries to be more greedy in the sense that on each node, when you compute the gradient, we in fact compute the error of the C sequential and the error of just C, and we send either C, either the gradient compressed with C sequential or with C, whatever is better in error. So the theory for this would be exactly the same, because in the theory, we only require bound to bound the error. And if we do better than C sequential, then the theory goes through. But in practice, this could be quite a bit better. We also have some handling of stochastic gradients, but I will not go there because that's really not that important to understand the novelty here. Okay, so now going to the theory of EF21. So first of all, and this is now answering Rustem's question. In fact, there is a relationship, and the relationship is pretty strong and pretty weak at the same time. So I claim here in this theorem that EF21 is equal to error feedback. So these are the same methods, but only for compressors which satisfy these three properties. And these three properties are not satisfied by practical compressors. So this is again of theoretical interest to understand that there is a class of compressors where these methods would be the same, but unfortunately this doesn't happen in practice. So for instance, the top K compressor is deterministic. There's no randomization there. It's positively homogeneous because if you compress positive multiple of some gradient, you get the multiple of the compressed vector, but it's not additive. So compression of A plus B is not compression of A plus compression of B. But you need all of these three for this to be true. And this also justifies why we call it error feedback. So we have two reasons to call EF21 error feedback. One is that it does what error feedback is supposed to do, which is it avoids divergence. So you could call any method which does that, error feedback if you wish, but then you'll be overwriting previous terminology of what error feedback actually means. When people say error feedback, they mean some particular method, but we're not doing that. We're not committing that disgrace here. What we do is we have a method which we can properly call error feedback because it is error feedback in this very narrow regime. So then we have two main theorems. The first theorem is this, and this is in the smooth non-convex regime. We assume that every Fi has Li Lipschitz gradients, and the average of the Fi's, which is F, is lower bounded. And these are the only two assumptions we need. So we don't need any bound on the gradients. We don't need any moment bounds. We don't need any bounds on the error throughout the iterative process, and so on and so forth. So these are very standard assumptions. And the rate that we get is some constant divided by t plus some constant divided by t. So it's 1 over t rate as opposed to 1 over t to the power of 2/3. So this is an improvement on the state of the art. So then we also have a faster linear rate if we additionally assume the PL condition, which is what you would expect of gradient type methods. And this is the first time an error feedback method achieves this without any additional assumptions or without additional tricks, such as using an additional unbiased compressor. Okay, and this is for some Lyapunov function, which I'll describe. Actually, I won't describe it. Yeah, I didn't include a slide on this. So now I will describe in a little bit more detail this first theorem here. So the rate magnified looks like this. And what we outputting here is a random iterate chosen from the first t iterates, uniformly at random. And we claim that the gradient of that is small. Here we have just the lower bound on the function, so infimum of f. G0 is just average of GI0. So these are the initial gradient estimators minus the initial gradients, local gradients. So if we set the initial gradient estimators to be exactly equal to the gradients, then G0 is 0 and the second term is not there at all. So maybe this is the best way to think of it. So you don't have this term at all, but this is not what you really want to do, because then you would need to communicate these full gradients at the beginning. So typically you want to compress even the first gradients and send compressed versions of them, and then you have this additional error because of that. All right, and then gamma is the step size, and for that we have this upper bound. So it's 1 over, so there's this -1 here, L plus quadratic mean of the local Lipschitz constants times some function of alpha, where alpha is the contraction factor. Because I'm just recalling the definition here. So you contract by 1 minus alpha. So one thing to notice here, if alpha is 1, okay, if the contraction is perfect, which means you incur 0 error whatsoever, which means that you are not really compressing, C is identity, then what happens here, you have 0. So you have 1 over 1 minus 1. So this whole factor here is 0, which means that this dependence on Li squares completely will disappear. So this whole thing goes away, and the upper bound on the step size is just 1 over L. So we perfectly recover gradient descent in the regime. This is also the first analysis of error feedback, which recovers gradient descent. And this is the reason why we can also obtain these improvements in the rates. This theta parameter is just 1 minus square root of 1 minus alpha. And if you have to compress at the beginning, which typically do, then you can essentially bound this by something like 2 over alpha, this 1 over theta. Okay, so I'll stop here because this is the main
there
slide.
are 2 questions. And by Sergey, I'll try to unmute you.
Yes, I ask, what is PL constant? What is PL?
Right. So in this term, I don't. This is not a regime where I assume the Polyak-Loryashevich inequality. This is the general theorem here, but you're referring to this table where in the second theorem we assume that F satisfied the Polyak-Loryashevich condition, which is a generalization of strong convexity. So if you're not familiar with the Polyak-Loryashevich condition, then just think of this mu as being strong convexity, and then you get linear rates, which you would expect for a function that is strongly convex. But it is known that gradient type methods in many cases would be able to achieve or are able to achieve a linear rate even if you relax strong convexity to the PL condition. And there are some functions which satisfy the PL condition which are not even convex. So this could be properly non-convex regime, but the regime which behaves as if the function was strongly convex.
And then there is one more question from Yegor. So he's asking, what about convergence of the last point? I think he's referring to this lemma right here.
Yeah, we don't have a theorem for that.
There's a question by Konstantin Vilachenko.
Yeah, thank you. I have a small question. Is contraction, i.e. alpha less than 0, essential for the proof?
So you mean positive, bigger than 0?
Yeah, I mean alpha less than 0.
Bigger than 0, right? Because alpha is positive, and the contraction is 1 minus alpha. So we need alpha to be strictly positive. If alpha is 0, if you don't get any contraction, then we get these divisions by 0 and so on. So we need that. So we need a strict contraction, not a weak contraction.
Yeah, I mean, if this coefficient alpha 1 minus alpha is greater than 1, so alpha is less than 0.
Okay. So you actually want this not to be even contractive. You want to even allow not going beyond 0 and even make it negative.
Yeah.
Well, all that we have, we need this to be strictly positive in the proofs. Yeah, but I could revisit this. So certainly in the strongly convex regime, we have a certain recursion, and we just keep multiplying something like 1 minus alpha, something slightly worse than 1 minus alpha many times, and that's how we get the linear rate. So we need that there, and but you are right that at least in the definition of C sequential, there it was certainly not important. Yeah, so we didn't ask the question, but there are issues certainly here. So if you allow alpha 0, then this doesn't really make sense and so on.
So we have another question from Nicholas, who is asking why for the second theorem there is no convergence to a neighborhood of the solution. Did you assume interpolation? So
second theorem, no. So first of all, we work with full gradients, right? So we don't have stochastic gradients here. And Nicholas is right that even in the case of full gradients, when you work with a method which is not with a compressed gradient method, which is not variance reduced in some sense, then you would expect convergence to a neighborhood. But one way to think of this, that this is variance reduced. It's not the right terminology here because variance is not the issue. In fact, these methods, these compressors have low variance. It's their lack of unbiasedness, which is an issue. But precisely because we do it in the right way, that we develop this Markov compressor in this sequential way, it will improve as you go on. And because it improves as you go on, you don't converge to the neighborhood. So in some sense, one way to think of this is something like the variance reduced method. but for contractive compressors, general contractive compressors. And that's why there's no neighborhood. Once you introduce stochastic gradients and you don't introduce variance reduction for the stochastic gradients, then you again will get some neighborhood, but this will not be coming from the compression, but from the stochasticity of the gradients. Any more questions in the chat?
There is no question, no raised hand. So.
Okay, so here's a quick corollary of this. So if the number of iterations is at least equal to 1 over epsilon squared, then the squared norm of the gradient is upper bounded by epsilon squared. So this is the right rate that you would expect, the same rate for gradient descent. And here you have the quadratic mean of the local Lipschitz constants, and here you have the contraction constant alpha. And notice again, if alpha is 1, which means you have perfect contraction, which means you're actually not compressing at all, which means you're running gradient descent, then this whole factor is equal to 0. So the dependence on L tilde disappears completely. So you only have L times twice the functional suboptimality divided by epsilon squared, which is exactly the rate that you would get for gradient descent. All right, so so we recover the rate of gradient descent, and this is also the first error feedback mechanism which does so. So now I only have a couple slides on experiments, and I already am running over time a little bit, but I'll be done quickly. So we run experiments also on some deep neural networks, but I don't have slides for those. You could look into the paper. They're not that important. What is important is to see why exactly this method works as when you compare it to error feedback. What is the reasoning? And this type of non-convexly regularized logistic regression is good enough for us to see where is the power of this method coming from. So the power of the method comes from the following plots. What we do here in each plot, this is the original error feedback, 2014, this is the new one, and this is the aggressive version where we do best of the two, best of the C or the C sequential in each on each node. So what we do, we run error feedback 21 with the theoretical step size. That's the first line here. K is equal to 1, which means we do top K, top 1 compressor, and 1 times means we have theoretical step size multiplier equal to 1. So if we run everything according to theory, we get this low convergence. So the theory is still pretty conservative, even though it's already improvement on the state of the art, which also by the way means that if you run original error feedback according to theoretical step sizes, there's no way you could really get anything. So then you increase by a factor of 8 or 16, 32, and here this orange line is increased step size by a factor 128, and the method still converges. And in fact, it's faster if you do that, if you apply that multiplier. For error feedback 21 plus, the effect is even larger, but then you get some oscillations in some places. What happens error feedback, the original one, is that yes, error feedback can get some boost from increased step sizes, but for some multipliers, it just stops working. So 128, it just stops working, cannot push the error below 10 to the power minus 4. So it's really what's going on that EF21 can absorb much larger step sizes because it somehow creates a more stable versions of the estimators of the gradients, and this is what is the main reason why convergence is faster. So now we did some comparison. Now in each plot I have all of these methods, including gradient descent. And then EF, that's the blue line, EF21 is the red line, and EF21 plus is the green with the triangles. And now we use the best step size in hindsight. So we fine-tune the step size multiplier. And for EF21, it was 16. In this case, by coincidence, equal to the same as EF. And EF21 is 256. So there we can take much more aggressive step size. And this also leads to the fastest convergence, EF21. Actually, no, EF21 is fastest here, and EF21 plus is not as fast. But all of these error feedback methods, all three, are much better than gradient descent in terms of communication complexity. So bits sent from workers to the master. And then you look at some other data sets and you can see you can have quite a bit of an improvement by using EF21 to the blue line. So the red and green line, or one of them or both, are essentially always better than EF. Eventually, if you're interested in highly accurate solutions. And we have observed this across all the data sets that we applied our methods to. Thank you very much for listening.
So yeah, thank you, Peter, for your talk. We are running a bit over time, but I think we can still take some questions. So please either raise your hand or put the questions to the chat. Just a quick clarification question for this plot. The error feedback, is it theoretical step size for error feedback or error feedback 21?
No, because there are no really theoretical step sizes for error feedback. The reason for that is because you need to have assumption on, say, boundedness of the gradients, and we don't know how the gradients will be bounded. We don't know that constant. We don't even know whether such a constant will exist. I mean, we cannot guarantee it, but we can only observe it as we run the algorithm, right? But then if we tune the step size according to the bound, we change the algorithm, so then maybe the bound doesn't hold. So this is just very difficult to get right. So what we did is that we simply assumed the same theoretical step size, which is actually computable, as for EF21. So the step sizes are the same.
And there's also one
theoretical from EF21, we apply it here, and then we start multiplying. And this is fair because we'll still multiply, right? So we can see how much we're underestimating the optimal step size. Yeah.
So then Igor is asking, at which point did you evaluate the gradient in the experiments? I guess whether it's to the last one or the average.
This is a great question, but to be honest, I'm not 100% sure, and maybe Ilias can say. I would assume it's the last one, but I'm not 100% sure. I'm just 90% sure. Is Ilias here? Igor? Last point, yeah, okay. Igor says last point, so he's right.